Let's see if we're online. How do I actually watch this? Okay. That looks a little bit better. Okay. Awesome. Hi, everybody. Hello. So, as I said, today we'll be doing another coding challenge. And I thought this would be a fun one. Because the first time I tried to kind of tackle it, I actually had a few problems. So that will be a fine issue to kind of tackle. It's been a long day. Okay, so the ancient Egyptians used to express fractions as sum of several terms where each numerator is 1. For example, 4 over 13 can be represented as 1 over 4 plus 1 over 18 plus 1 over 468. And if you think about it, the best approach is what people call a greedy algorithm, which means let's find the biggest fraction with a numerator 1 that is still smaller than the value we have. So we can do import fractions, right? And do, this is kind of a nice trick, right? Because then if we do this, then it automatically turns into a fraction, and it's kind of a nice syntax. So if we look at a fraction like 4 over 13, like 1 times 4 over 13, right? Then the way to find what's the biggest numerator is to kind of reverse a fraction. Reversing the fraction just means doing 1 over. And then checking what the numerator is. Denominator. And then we can just do an integer division, right? So if we do that, right, if we do 13, we almost get the right value, right? It's not 3, it's 3, and we really wanted 4. So why did we not get the right value? Because integer division rounds down. So we want something that rounds up. And the easiest way to do that is just to do, there's a bunch of ways to do that. One of my favorite is to add n minus 1. 4 minus 1. Right. So let's define this operation, right? Def find biggest part, we'll call it. And that's gonna be some value. And what you want to do is do inverse equals 1 over val. And then we want to take inverse dot, we'll just do this so that it's easier to kind of understand. And d equals inverse numerator inverse dot denominator. And then we'll do n plus d minus 1 floor division n. We'll call it like denominator, we call it ret denominator, and then we'll do return 1 divided by ret denominator, and let's check that it gives the right value for biggest part. Oops, that didn't work the way we wanted it to. Let's just make sure that this is the right value. Yeah, okay, so let's figure out what happened. Let's do print inverse here. Okay, so the inverse is right, N and D is right. Oh, divide by D. Yes, that was my mistake. Yep, now it's a quarter as it should. Let's remove this. And we already used this to debug, so we don't need this. Okay, now we have this. Okay, so now let's do get Egyptians val, and we'll write a little helper function. We'll call it get Egyptian string, and we'll notice that if value is 0, right, then basically it's a 0 length list. So while value is not 0, we'll do part equals find biggest part val, yield part val, okay, and now to debug it we need to do list of, so list of get Egyptian stream, and we'll do 1 times 4 divided by 13. Okay, and we got exactly what we wanted. Quarter, 8, 468. But that's not formatted the way we want it, right? So that's okay. All good. Right? We made some progress. So now let's do get Egyptian, and get Egyptian won't have to do let's do this. Stream equals list of get Egyptian stream of 1 times 4 divided by 13 stream. Beautiful. And now let's write a function called format stream. And we'll call these things parts. So we'll start by saying something like part dot numerator divided by part denominator we'll do it in a few iterations. So let's do for part in parts. Let's do, this is why I turn it into a list, so I can run this function multiple times on the stream. Okay, so that looks nice, right? Now all we need is to join it. Join. And we got the format we wanted. Now we just have to put the parts together. Okay, so def get Egyptian Okay, so what's the benefit of, and let's just kind of test it out to make sure that we did it. Egyptian of 1 times 4 divided by 13, and we have the result we wanted, right? If you look at this, right, we can now delete this. Right, so that was pretty straightforward, right? The only trick is to remember the plus d minus 1 here, otherwise you get the wrong value. But other than that, that was kind of straightforward. And part of the benefit of breaking these two into separate functions that we only put together here is that if you imagine we would write unit tests for them, writing a unit test for that is pretty straightforward, right? You just put a stream and you know what the result is. And writing a unit test for this is pretty straightforward, right? You can just literally add all the parts and see that you can see that each part is just 1 over, and that if you add all the parts, you get the value, right? So the unit test for that is pretty straightforward. The unit test for that is pretty straightforward because it's just string formatting, but the unit test for that would be annoying. But this function can't have a subtle bug, right? It's just combination of two functions. If each of these functions works, and this works for one element, and it will always work. There's no corner case, right? You can wonder what the error case here, for example, if parts is say empty, is it okay to yield an empty string? Maybe you want to work around that. You'd have to write a real code here, right? Maybe here you'd want to first check that value is not less than 1, or that value is actually a fraction or something. That's also reasonable, right? So these functions can have bugs, right? Even the way I wrote them, there's some arguably bugs, right? Like, you would, of course, ask your interviewer, can I assume it's always positive? Can I assume that we're giving a function? What kind of input will the user actually input, right? These functions can have bugs. This function can't have a subtle bug. If it works for one thing, it works for other things. So we don't have to be very careful about unit testing that. And here we can be very, very careful with unit testing because writing a unit test for those is very straightforward. So this is kind of like a good way to show that even if you're not writing tests, right, this would be a good code because that code is more amenable to writing good tests, right? Tests that don't assume anything about the implementation, tests that are pretty simple in and of themselves, right? Summing things up and checking that they're all numerator 1 is very straightforward. It's much simpler than the algorithm, right? It doesn't even call find biggest part. Writing a unit test for find biggest part is also straightforward, right? You check that the numerator is 1 and it's less than value, right? It won't check you that it's the biggest part, but at least it will do some of the work in testing that, right? And it doesn't have to do any of the complicated think about division, right? So you want to write functions whose unit tests are much simpler than the implementation, right? Because you want most of the code ideally to be in the code and not in the test. Sometimes you have to write complicated tests, but you want to make sure that your code is a minimal test, right, which are as simple as possible. But yeah, that's kind of like all I have to say about that, pretty much. I think this is pretty much the optimal implementation. I don't think we can improve it by much. I mean, someone can say, why don't you just call, the constructor directly? And arguably, you can argue which way is better, right? It still gives the right result, right? You can argue which way is better, right? This way you don't have to use one, like the constant one. It's kind of weird, but in some sense you are using another constant, you're using this constructor. And you're kind of using the constructor in the same way, right? This is pretty much equivalent to this, except it constructs one less object. But since one was already constructed, oh, I'm busy right now, okay? Okay. Yeah, so sorry about that. So you can argue which way is better, but I actually think that the most readable code is just to define one, and then you end up writing kind of the mathematically natural code, right? One over a denominator. This is how you do it if you're just like writing math. And I like my code to resemble the mathematical stuff I'm doing. So this is it. This is a solution for this. I hope everybody had fun. It was a bit shorter than usual. The code was a bit more straightforward, but I got a chance to talk a little bit about how to write testable code. Anyway, if you have any questions, please reach out to me. You can go, I will put it in the notes, but if you go to cobordism.com, you can find every single way to get in touch with me, known to humankind. Literally, that's my email, my Facebook, Twitter, Instagram, LinkedIn, Pinterest, Keybase, Flickr, Reddit, Google Plus. I think they removed it. I should probably remove it from the stuff. Mastodon, Discord. You can subscribe to my newsletter. You can find my books. You can find other open source. You can get in touch with me in GitHub, GitLab, Bitbucket. You can see my stuff on Docker Hub, Quay with the Dogs, PyPI, Stack Overflow, even the comprehensive Tech Archive network. So anyway, and of course, if you want to get in touch with me over the wiki quote, you can do that. I'm no longer much active there, so I'm not sure if that's very useful to you. Anyway, hope everybody had fun, and I will post this on YouTube later and post another link. So if you didn't catch it live, hopefully you can catch the recording. Bye everybody.